Okay, picking right up where we left off. So I had gone through an analysis of thinking about a container filled with gas with a constant number of moles of the gas, but different pressures, different temperatures, different pressures, different volumes, and therefore correspondingly different temperatures. I calculated all of them, and then I asked the question, what can I say about the process, and literally the physical process, of changing the state of my gas from one combination of P, V, and T to the other combinations of P, V, and T. And I pointed out that it was certainly possible to change the state in multiple ways. And I've only drawn a couple here, but there's lots of possibilities in Printable. There's an infinite number of possibilities, but only a few are of actual practical interest to us. And I said one possibility is that I could start my change, let's say going from state 1 to state 2, from the purple dot to the blue dot. I could go directly from state 1 to state 2, but if instead I, for my reasons, decide to start off by simply changing the pressure of the system, but somehow preventing the volume from changing while that happens, and then having achieved the pressure that I want, then allow this system volume to change, but now keeping the pressure constant, and keep changing the volume until I get to the second state where I want my system to be at. And then going from 2 to 3, I could instead just let it relax sort of directly, except it's not just arbitrary. I'm going to let it relax simultaneously losing pressure, simultaneously losing volume, going to the left on the horizontal axis, but doing it in a carefully controlled way so that the temperature never changes. Okay? And so, in other words, we have three possibilities. I can have a change of the state of my system, a change of state that keeps the volume constant, or that keeps the pressure constant, or that keeps the temperature constant. Not too difficult. You got to think about it for a while, kind of wrap your head around it, but you get it. No, and I said at the end of the last lecture that, of course, we physics teachers hate you and want to make this harder than it needs to be, just to prove that we're smarter than you, because we have very poor self-images. Okay? And so one way we do this is to invoke Latin, or possibly Greek. I think it's Latin. Anyway, any normal human being, or at least any normal English-speaking human being, would say, oh, it's a constant volume process, it's a constant pressure process, it's a constant temperature process. Latin. Okay. Constant pressure, there's new names. This next bit is vocabulary. So if the process that happens is constant pressure, we call this isobaric. And the problem is, I'm going to give you a bunch of names, and who can remember them all? The best thing I can suggest is to think of other words that maybe you do know already that kind of have the same root, and try to remember like that. So isobaric, well, the BAR is the key syllable there. And so barometric pressure, barometer, those are the ones I can think of. Those things are all about pressure. Okay. So, and as far as, and then ISO, what in the world does ISO mean? ISO refers to self, or the objects in question. In other words, for like isolated, so it's just a single person, right? And so an isolated pressure, or a single pressure. Oh, constant pressure. There we go. All right. Similarly, we have, if we talk about a constant constant temperature, the word here is, I'm sorry, I need to pause recording just 1 second. Sorry about that. At a constant temperature, it would be isothermal. I probably don't need to explain that too much. And then finally, and this is personally my favorite one because it sounds so cool, and it's a word you'll never ever use except in this context. Constant volume. So constant volume, this is this stage here. Okay. We allow the pressure to change, but we don't. But we keep the volume constant. This one is a great word. I love this word. Isochoric. And as far as this word, isochoric. As far as this word is concerned, the only way I can remember that isochoric means constant volume, because I know it isn't the other two. There's only three possibilities: constant volume, constant pressure, constant temperature, P, V, and T, right? I know isobaric, I know isothermal, I know isochoric isn't the other two, so I know there's only one left. It's got to be volume. Fantastic. Now there's one other constant way we can change things with and keeping one thing constant, and it's not visible here, and that'll be later. But for now, this is good. So this process here, I would call this is an isochoric process. This process here is isobaric. This one here is an isothermal process. Okay. This is mostly vocabulary, as I say. You'll run across this sort of stuff in your future lives, and so that's it is. But the reason behind all of this stuff is you often want to control how your system changes, how it evolves in time, in changing from one collection of pressure, volume, and temperature to another one, based on whatever your physical system here. Because after all, think about it. If you allow the pressure to run wild, if you've got some delicate equipment, like for example, if you've got some sort of life form or a cell or something that you're keeping inside of a gas because you're investigating the structure of the cell or something, and if you allow the pressure to fluctuate wildly before in time scales smaller than the time that the cell can adapt to the changing pressures, you could destroy the cell you're investigating. Same thing with changing the temperature. You may not want to change the temperature so that you don't denature your proteins or something, right? So you will control these various things depending on what particular experiment you're trying to run. That's why we care about this sort of thing. Okay, and so you're doing your job and everything, and your boss says, make sure that this is an isochoric process, so that we don't screw everything up and have to redo 3 weeks worth of data, right? So you need to know what these vocabulary terms are. And a constant temperature one, because of considerations similar to what I was just describing, constant temperature ones tend to be perhaps the more common of these things. And so let me talk about that a bit. So let's look at constant temperature or isothermal process. So this isotherm implies that T is constant during the process. By process, by the way, I mean the change of the state of the system, the change of state, as we say. By change of state, I'm simply saying, I'm talking about the changing of the pressure and the volume and the temperature. Okay, so the change of state is shorthand for that. So T is going to be constant. That means from PV equals nRT, right? Then the pressure is related to the volume. The changing pressure is related to the changing volume. What's the mathematical relationship? Well, N is, we are assuming that the number of moles that we have inside of our container is going to be constant. We made that assumption a while ago. R, of course, is a constant by definition, and we are assuming here that T is in fact constant. So this whole thing in blue is a constant, okay? And so, P is related to the changing pressure is related to the changing volume as a reciprocal relationship. Okay, and you may remember from one math class or another that the plot of a reciprocal like this, P versus V in this kind of a relationship, graphs to a hyperbola. And this hyperbola is an isotherm. A what? An isotherm. This curve here is given the name an isotherm. This is another vocabulary term, and what that's shorthand for the curve on a PV, on a pressure volume diagram. Oh man, I got to tell you, you may have already picked up on this. This entire topic is so flooded with terminology and shorthand, it just drives you nuts. And I'll sort of expose you to a little bit of it here. Okay, so isotherm, that's shorthand. Shorthand for what? That on a pressure volume graph, where with the assumption that the temperature is constant, then the pressure, the pressure as a function of volume graphs to a hyperbola, and this hyperbola is the result of assuming that the temperature is constant. Temperature of constant means isothermal process. So this line, this curve, is an isotherm, a line of isothermal process is what that is shorthand for. Everybody calls it an isotherm. Okay? So far so good? And this could be the result of, for example, requiring that T be a constant, I'm making up numbers here, 200 Kelvin. On the other hand, if you had the same physical system, but you wanted to, oh wait, I should do this. No, wait, I should do this. Let's do purple, right? State 1. State 1 is a constant temperature of 900 Kelvin, let's suppose. Okay? And actually, I probably shouldn't do that because I don't want you to think, well, whatever. Okay. State 2 is at a constant 3600. And state 3, constant 600, perhaps. Okay. Now, I don't know that these, I was just kind of making things up. I don't know that these diagrams actually properly correspond to the volumes and pressures. They almost certainly don't of the various states. So don't try to correlate these two closely with the previous example. The only thing I want to get at is that the temperature of my system as the pressure drops and as the volume increases, the temperature of this system here stays at a constant 600 degrees the whole time that the pressure is dropping and the volume is increasing. This state here stays at a constant 3600 the whole time P and V are changing. This system stays at a constant 900 Kelvin for the whole time. So this is a family now. Here's more terminology. This is a family of isotherms. And if that's not enough terminology for you, this whole thing here is known as a PV diagram. So you say stuff like, draw the family of isotherms on a PV diagram for this system, and then for the next several temperatures. That's what this is. Okay. So the answer then to my original question that I stated a long time ago, which was, does it make a difference how the system gets from state to state to state, is yeah, it absolutely does. Because going from state 1 to state 2, you can keep the pressure constant, you can keep the volume constant, you can keep the temperature constant, let them all change together, and it will turn out, which I'm not going to go into this right now, perhaps we'll talk about it in class, it turns out that the amount of work that you do on the system or the amount of work that the system does in allowing the gas to expand or the gas to contract. Of course, that's the displacement of the particles, so that's work done. From the pressure, it applies a force on the particles. They expand, they contract. That's work done. So work done either on the gas or work done by the gas. Positive work, negative gas. No, sorry, positive work, negative work. The gas gains energy or the gas loses energy. Lots of different combinations, but what happens in all those cases depends strongly on whether your process is isobaric, isothermic, isochoric, or none of those. Okay? And exactly when you do which, how often you do the other, why you do the one, why you do the other, depends entirely on the system you're working with, exactly what your goals are, why you want to do one thing versus want to do another thing. So that's what that is. All right. Well, that was an awful lot to think through. So now the question is, what now? Well, these are gases, and this is how they respond to changing pressure, changing volume, changing temperature, stuff like that. What if it's not a gas? What if it's a liquid or a solid? Or how do the rules change? How do the concepts change? Quite a bit, as it turns out. And it turns out solids are rather easier than liquids, and so we'll take up solids